Good morning. Okay, so I got you guys to watch a portion of the video. If you ended up watching the entire thing, then we're going to go through that example again. So if you've seen that, then you're all set. But we're going to work through that example together. So let's see here. I have posted the tables. Okay, so you've got this tables and it looks like this. Okay, so and if you're in town, I have printed copies of the tables if you want, so you don't have to print them off. Otherwise, it might be nice to have it printed off, or I mean, if you're working on a tablet, you can just kind of write on it that way, and that's nice. But we're gonna kind of review the table today, and I just wanted to show you that it's there. Okay. So let's see here. Just for a quick note on the quiz. So you guys did your quiz and that's great. And what I do afterwards, after you write the quiz, especially for the first quiz, is I go through and I make sure that you have all the marks that you should have. So I'm lenient on things like if you didn't follow the rounding instructions for the first quiz, I expect you to follow the rounding instructions, but for the first quiz, it's okay. And then I'll make adjustments. So, but it's not as urgent as some of the other things that I'm working on, because your grade can really only go up from where you're at. And I have a couple of emails already where you've gone through and had a look and said, oh, I don't know why I didn't save this answer or something like that. So so I'll go through on the weekend and just kind of sift through all that and make sure that everything's all good. So I'll let you know once I've checked those quizzes, and then if something is still off, then you can let me know. And I know that it was on the long side. There's a reason for that. So they will always be a little bit on the long side, okay? Because what I would prefer to do is make them long and kind of challenge you, okay? Well, okay, so for your written work, it's really just so I'm getting a couple of messages. So it was too long. Yes, I know. That's on purpose. Okay, so they will always be on the long side. So you have to keep your pace up. And so the reason for that is because you have to know this stuff, right? So the purpose is, okay, you're working on a problem, you should just know how to do it, right? Even though it's open book and you have access to materials, right? The goal is that you should know what's going on. Okay, so I'll always make them a little bit long, and then I'll deduct some of the total if I feel the need to, right? And that's after I've looked to see how everyone did as a class. Okay, so you know, if it was too long for everyone, then of course I'm going to scale that back. Okay, but just be prepared for something on the longer side, right? And honestly, it's because it makes it harder to cheat, right? If it's long, then it's really difficult to cheat. So and that's just something that we have to deal with, right? And so I'd rather make it a little bit too long and then kind of fix it after the fact. Okay, so for your written work, I'll have a look at the written work. It's possible, so it's just a record of the things that you're writing down. So you can do like 1A, 2, 3, something like what the answer is. Okay, that's, yeah, so I'm getting these direct messages. How about you let me deal with the quiz before we start talking about what I need to do? Okay, so I'm going to have a look at it. and we'll revisit after, okay? Because you don't know yet what I will or will not do with it. All right, remember, we have 4 quizzes in total. So that was just the first one. And of course, the first one is going to be hard because you don't know what to expect, but I think you'll improve. Okay. All right, so let's see here. So you watched the video last day, which goes through, because I don't do any of this kind of preamble talk about quizzes and stuff like that in those recordings. I am able to cover a lot more material, and so that was a good way to introduce you to the normal distribution. Okay. So in terms of review, let's see here. Let's do a tiny bit of review. We've got a big example to work through. So we'll just review a little bit. Okay. But what we said was that the normal distribution is a special distribution that we're going to be using. And our goal is we're going to use the normal distribution to find probabilities. Okay. And so we will use the normal distribution to find probabilities. How was that? Well, let's see, I might need a little bit more space there. But the normal distribution looks like this. And what we said was that the area under the curve, right? So the area underneath the normal curve is a probability, right? Or those are probabilities. So the area under, under the curve is a probability. Or are probabilities, I guess, but it doesn't really matter. So the area under the curve is a probability. Now, that means that the total area under the curve must be 1, right? And we're going to leverage that a lot. Okay? So therefore, the total area under the curve is 1. I just remembered something. Let me just write that down. Sorry, just remembered something I had to do. Okay, so the total area under the curve has to be 1. So what can we do? Well, so if we have something that follows a normal distribution, then we're going to have a mean and a standard deviation. And that describes the whole distribution, right? It means that we know the shape, which is normal. We know the center, which is the mean. And we know the spread, which is the standard deviation. So a normal distribution, a normal distribution. And one thing to notice is that sometimes I'll capitalize the normal distribution, so capital N, and sometimes I will not. And I often just capitalize it to emphasize that it's a name, right? But you can use a lowercase normal if you want. But in the beginning, I find that it can get confusing when we say normal distribution because it is a shape, right? Just like this is a square and this is a circle and this is a rectangle, right? This is a normal distribution, right? So those are names, but you don't have to capitalize them, right? So same thing. Okay? So a normal distribution can be described using two parameters. Can be described fully using two parameters. Mu and sigma. Mu is the mean, the population mean, right? Sometimes we'll be a little bit wishy-washy here, but as soon as you have a Greek letter, you know that it's a population measurement, and sigma is the standard deviation. The population standard deviation. Okay? And so what we said was that, okay, if we draw some measurement and it comes from a normal distribution with a mean mu and a standard deviation sigma, so assuming that we know something about the population, which we're going to assume, but that's not always the case. But for us, we're going to assume that we do. Then what can I do? I can standardize those values, right, in order to find the areas under the curve, right? Because otherwise we would have to have probabilities calculated for every single mean that we could have and every single standard deviation that we could have, and it becomes an infinite number of probability tables, and we don't want that, right? And so what we do is we can use a standardized value. Okay. So a Z-score, and maybe I'll say a Z-score. A Z-score is a standardized value which measures how many standard deviations a measurement is from the mean. Is a standardized value which measures how many standard deviations a measurement is from the mean. So we said, okay, I can calculate a Z-score, right? And this is to standardize the value. So Z equals X, which is measurement, minus mu divided by sigma. X is the measurement. Okay, let's see here. This is the measurement that we're interested in. So that's this guy here in that blurb. Right. Mu is the mean. Okay. Sigma is the standard deviation. Which measures how many standard deviations. And what we said, oh, I have to use a color I haven't used yet. Let's say this one, blue. Z is a standardized value. Oh, would you mind? So instead of sending it directly to me, would you mind resending that question? The measurement would be the value or an observation. Would you mind sending it to everyone so they can see it, please? And then, awesome. So a Z-score is a standardized value. Okay, so the Z-score is a standardized value. Thank you. Awesome. So the question is, so the measurement is a value, okay? And it's one value from an observation. So I guess the answer there is both, a little bit tricky, right? But this measurement is going to be the value that we're interested in, finding the probability associated with. Okay? So here, X, the measurement, is going to be the value we want to find a probability associated with. The value we want to find the probability. And just to simplify things, I'm going to say probability for. Okay. For example, right, if I know the distribution of heights in the population, then I know the mean and I know the standard deviation, right? And then a specific question would say, okay, what's the probability of finding someone who's shorter than 5 feet, right? Or I don't know, 150 centimeters would be about the same, I think, but I don't know. Right, and so it's funny because I am metric, but then for heights and weights, because I've lived here for so long, I am mostly imperial, and it's weird. But anyways, so 150 centimeters, what's the probability of being shorter than 150 centimeters, right? And so what we would do is we would take that 150 centimeters, because that's the value that I want to find a probability associated with. And then I would find the distance from the mean, right? And then I would divide that distance by the standard deviation, right? And so, yeah, so the 3, I suspect, is talking about there are 3 standard deviations underneath the curve before the tails get so small, right? And remember, the area under the curve is the probability, right? And so the area under the curve continues from positive infinity to negative infinity. And so it never closes on the axis, which can get confusing, right? Because we also know that the total area is 1, right? And so that gets hard to wrap your head around, right? But the key thing to remember is that the tails never close on the axis, right? So there's always a probability, but in the main chunk of the distribution, you can fit roughly 3 standard deviations on either side of the mean. Right? And then the probability gets really, really small, right? So it depends on what the mean and the standard deviation are, and then we can find the standardized value. Right? So then we use the standardized value. We use the standardized value, which is the Z-score, to find probabilities, right? To find probabilities, which is the area under the curve. But now we're going to focus on the standard normal curve, which is the area under the curve. Oops. But here, now we're talking about the standard normal curve, which is the distribution of Z. So Z follows a normal distribution with a mean of 0 and a standard deviation of 1. Okay. If you think about it, if a measurement is the mean, right, whatever the mean is, how many standard deviations away from the mean is it? It has to be 0, right? And so if a measurement is one standard deviation away from the mean, once we take into account the standard deviation, that would be one standard deviation away from the mean, right? And so that's where we get the 0, 1. So what happens is we're able to take any normal distribution with any mean and any standard deviation, and then we're able to shrink it down to a mini version of it that looks like a normal distribution, and it is, with a mean of 0 and a standard deviation of 1. Okay, so that's going to look like, and I'm going to keep it on the same page here. For when I save it, 3 standard deviations and 3 standard deviations, roughly, right? But they also, it continues to negative infinity and positive infinity. So that's not what I'm saying. It's for the bulk of this area here, we can fit 3 standard deviations. And that's always true. Okay, so we are going to use the table, and that's only because I don't want to be going back and forth to RStudio Cloud to show you the calculations one by one, because that would be very time consuming, right? And especially if you're working on questions and maybe you're not working on your computer, or you just don't want to be using software for whatever reason, then you can use the table, right? And so imagine we're in person, or if we were in person and we had an in-person test, then I would make you use the table, right? Because then you don't need access to a computer. Using the tables is very old school, right? And so it's not something that you're going to be doing in life, but software is going to give you the same values, right? So for us, I'm going to show you using the Z table, and then I'll show you how to do it in R as well. And it's easy to find out how to do it in Excel, for example, right? And so whatever you prefer. So to find probabilities, we will use the Z table. Okay. The Z table is kind of old school. The Z table is old school. And in practice, so out in the real world, you would use software. Is old school. And in practice, you would use software. But the values that you get would be roughly the same. The only drawback is that the table limits you to 2 decimal places for Z, and it only gives you 4 decimal places for the probability. And so it is limited in that way. It only goes from negative 3.49 to positive 3.49 for the Z scores. And so it's limited, but we can still answer all the questions with the table. Okay. So what does the table look like? Let's do a little reminder here. So I like this version of the Z table. There are many, many versions that I've seen. I like this one because it highlights some definitions, right? So the table entry is the area to the left of whatever Z you feed it, right? And it even has the description here. So the table entry for Z is the area under the standard normal curve to the left of Z, okay? And so Z, you're gonna find your first whole number and the first decimal, your whole number and your decimal, your first decimal in the left-hand margin, right? And then you're going to join it up with the second decimal of Z, okay? And so here, these values here These are the table entries. Oops. Okay. So it's going to go from, so it's centered on 0. If the total area is 1, then half of the distribution must be below 0 and half of it must be above 0, right? So we can show that here. So 0.5, 0.5. Notice how if I know the area to the left, then I leverage the fact that the total area must be 1 to find the area to the right. So the table will only give you the values to the left of Z. And that's really important. And so the table maxes out at negative 3.49. And at negative 3.49, the area to the left is 0.0002. So here, 0.0002. By symmetry, okay, I know that, well, then the area to the right here must be what? Must be, sometimes I draw it up higher, but I'll just go from here. Must be 0.999, oops, missing a 98. Okay. Right. So I know the areas on either side. So depending on the question that I want to answer, right, then I can just calculate it if I need the area to the right. Similarly, on the upper end, it maxes out at 3.49, and we're told that the area to the left is 0.9998, which means the area to the right is 0.0002, right? They're symmetric. Okay. Notice, so it's really important, right? It extends to positive infinity and negative infinity, right? So it's possible that you have a value of a Z-score of maybe 12 or something like that, right? But what does that mean? That means you're way out here in the tail. All we really know then is that the area is less than 0.00002, which I would just shorthand to approximately 0. So it's a pretty extensive recap. Let's get into an example. How do we use this? Let's see here. It's split over. Oh yeah, and I think I maybe mentioned it in that video, but I do have the R code in these notes as well. So you use in R, you use the p-norm command. It needs the measurement, it needs the mean, and it needs the standard deviation. And then it's going to give you the area to the left, just like the table. Okay. Oh. Trying to keep it there. Okay. So the example we're going to use to illustrate all the things that we can do here is about a cereal manufacturer. And this goes for, you know, any sort of production that you do, anything that you sell really, where you have to list the weight or the volume, which is a lot of things, right? Then you're going to have this, this scenario. So a cereal manufacturer has a machine that fills the boxes. The boxes are labeled 16 ounces. It doesn't matter. So most of the examples that I've stolen are from American textbooks, and so they will have imperial measurements. I don't know how much 16 ounces is, but I know how much a cereal box is, so whatever. So the company wants to have that much cereal in each box. Okay, so when you go to the store and you buy a box of cereal, you understand that it's not going to be exactly the weight that's listed on the box, right? But you expect it to be roughly that weight, right? You understand that it's going to be potentially a little bit less or a little bit more than what's listed, right? And so what we need to do is, as the manufacturer, we need to make sure that it's satisfying that criteria, right? Where customers aren't getting upset because there's not enough in the boxes. Customers don't get upset when there's too much in the boxes, right? But if I'm the one making money off of this, I don't want too much going out in the boxes, right? So we have to find that that happy medium. Okay, so if the machine is set at exactly 16 ounces and the normal model applies, then about half the boxes will be underweight. So in this case, a box would be called underweight if it was less than 16 ounces, right? So we don't really have any wiggle room there. If you took a cereal box and it said 16 ounces, you came home, you weighed it, and you find that it's less than 16 ounces, you would say that it's underweight, right? So that makes consumers unhappy and exposing the company to bad publicity and possible lawsuits. It really kind of goes into it. To prevent underweight boxes, the manufacturer has to set the mean a little higher than 16 ounces. And there's a typo here. That's okay, I'll fix it. Based on their experience with the machine, the company believes the amount of cereal in the boxes fit a normal distribution, so that's the shape, right, with a standard deviation of 0.2 ounces. Okay, so we know the shape and the standard deviation, and the manufacturer decides to set the machine to put an average of 16.3 ounces in each box. So before we go ahead and do this example, let's just have a look at what happens. So if we have it centered on 16, right, then all of this, let's see here, then these are all underweight. So if it's centered on 16, what's the probability of getting an underweight box? The probability would be half, right? 0.5 or 50% if you want percentages. So, right, because half of the distribution is less than 16, right? So what we do is we want to minimize this area, right? We can't minimize it to 0 because then I'd have to overfill the boxes a lot, right? Which I don't want to do. So what we do is we shift this curve, shift it like this. And so now what they've decided to do is if I center it on 16.3, right, remembering that this axis here is the number scale, so the weight of the boxes, then I would have 16 here, right? And so now only this many are underweight. Okay. So the questions that we're going to solve involve, okay, figuring out what's the probability of having an underweight box and just kind of working through that. So part A, what proportion of the boxes will be underweight? And I'm going to steal each of these. Oops. So what proportion of the boxes will be underweight? So what we need to do is we need to use this curve here And we actually want to find what proportion or what percentage or what's the probability of having an underweight box. Remember, proportion is the same as a probability, so that is the area under the curve. And then if you prefer to report percentages, that's fine. Okay. So what we have is we have this normal distribution here. And we're told that it's centered on 16.3. And then I'm just going to jot down that the standard deviation was 0.2. There's no real way of properly showing it on the graph. It doesn't really reflect directly in the graph, right? But we know that the bulk of the data is going to be within 3 standard deviations, but I don't want you to worry about that, right? I'm just going to focus on using it in my calculations. Okay. So if I have 16 here, what proportion? Well, that's going to be the area under the curve, right? Because that's a probability, and a probability is a proportion. So usually what I do to indicate what I'm solving for is I put a little question mark here. Okay, so the first thing you're going to do is you're going to draw out these questions and draw out all the information that you have, and then you're going to go ahead and solve the problem, right? So first thing you have to do is draw it out. And especially when you're just starting out with these problems, you won't want to draw them out, right? I know you're not going to see the value in it, but what I want you to do is just always try drawing it out, right? Just try drawing it, and eventually the drawing will help you, right? You're not going to feel like it does in the beginning, but if you stick with it, it will help you solve these problems. Okay. So the proportion is the percentage and it is the probability, and that's the area under the curve. So we want to know, what is that area? Okay. So the first thing I have to do is I have to identify the measurement that I'm interested in, right? And that's going to be this 16. That's the value that I want to find a probability associated with, right? Or a probability for. So in my calculation, I'm going to have Z equals X minus mu over sigma. So I need to figure out how many standard deviations is 16 from 16.3 if sigma is 0.2. You could probably do it in your head, but that's not always the case. This is obviously a very, very basic example that we're working through, very kind of organized, right? So 16 is your measurement because that's the value that you want to know the probability associated with. How far is that from 16.3 in terms of the standard deviation, which is 0.2? So here, okay. So 16 minus 16.3 divided by 0.2 puts me at negative. So Z is negative 1.5. And I'm going to add a 0 because Z scores go to 2 decimal places. Z scores need 2 decimal places, right, to use the table. Okay. Okay. So now, what does this Z score tell me? If it's negative 1.5, then I know that I'm 1.5 standard deviations below the mean, right? The negative just says that you're below the mean instead of above the mean. Okay. And so I have to keep that negative. It's very important. Okay. And it makes sense with my drawing, right? 16 is less than 16.3, so it should be negative. Okay. So now I can go to the Z table, and I'm going to grab it. Grab a portion of it. So I can draw on it here. Later, I won't pull it in, but it's nice for this first example to have it. So the first part of the Z is the negative 1.5. Okay. So that negative 1.5, I go and I find it here, negative 1.5. So let me just take that up here. Okay. The next part of my Z-score is the 0. So the second decimal of my Z-score is 0, which is just right here, right? If it was negative 1.55, right, then I would go here. But it just happens for this very easy example, or basic, I should say, it's just 0. Okay. So even if you have a Z-score with more than 2 decimal places, you're going to need to round it to 2 decimal places properly, right? If it's more than 5 or including 5, then you have to round up, right? Or if it's less than 5, not including 5, then you have to round down, right? Basic rounding. Okay. So then what I do is usually I'm gonna just draw a line, the entire line at the value, the first kind of part of Z that I want. Okay, because usually you're going to be over here with these decimal places, something other than 0. So then what we need to do is we need to join these up, in this case with the 0. And then the intersection is the probability. What probability? It's the probability to the left, right? It's going to be the area to the left of this Z-score. So what we have is we've taken, and I'm going to copy this and only steal a little bit. Copy. Okay. I'm going to keep this. Okay. So we took this, right, original distribution, and then we converted it to a Z-score, negative 1.50, which makes the same graph that we had. In fact, maybe I'll just copy it. And these values are no longer Z is centered on 0 with a standard deviation of 1. And this Z-score is negative 1.50. But notice how by calculating the Z-score, we've standardized this 16 with respect to the mean and the standard deviation, but the area that we find is going to be the same. So that's when we can just say, okay, well, if the probability associated with the Z equal to negative 1.50 is 0.0668, then that's the same probability for 16 with respect to 16.3 and a standard deviation of 0.2. Okay. So what we find here is that this area, we're no longer kind of wondering what it is. It is 0.0668. 0.0668, which means that this is the probability 0.0668 of finding an underweight box. Okay. Usually I get lazy and I don't interpret the probability. I just write down the number, and that's okay if you do the same thing. The purpose here is to be able to find probabilities, right? Later on, we're going to focus on interpretation, but therefore the proportion or probability, right, because they're the same, the proportion of underweight boxes will be 0.0668. One thing that I want to mention is the table gives you 4 decimal places. And I know a lot of you are going to want to round that value, but do not round it. Okay, you have to keep all those 4 decimal places. We've already rounded our Z-score, so we don't want to do too much rounding because then our answer becomes way different, right? So keep all 4 decimal places there because you already kind of introduced some error if you had to round your Z-score to 2 decimal places. Nice. So the next part, oops. What proportion of boxes weigh more than 17.21 ounces? So we're going to do the same thing again, but what I'm going to do is I'm going to show you kind of a quicker version of writing out your work, because this, how I did it here, I just wanted to show you what was happening. But typically we only draw this first curve, and then I know that this 16 has been transformed into a Z of negative 1.5. So then I usually only draw the one curve. In some of those practice problems that I posted at the bottom of Moodle, which are just extra practice problems, they're not for anything, they're just for you, with worked out solutions, they use the Z distribution, and that's fine. It was just because I don't want to have to change the programming for every single question. I just want to use a Z distribution, but either way, they turn out the same answer. So how can we answer this question? Well, first thing we're going to do is we're going to draw the graph. So I know the boxes still follow a normal distribution. They're still centered on 16.3 and sigma is still 0.2. So what I want is I want the 17.21. That's the area that I'm interested in, right? What proportion of boxes weigh more than 17.21? So 17.21 in terms of a number scale, right, would be on the higher end from 16.3. So I get 17.21. Notice that I don't put a lot of thought into where I draw the line. I want to show that 17.21 is above 16.3, but I paid no attention to how far it would be with respect to the standard deviation. I let the Z-score tell me that. So drawing the curve is really just to help you visualize, okay? And so what proportion of boxes weigh more? Well, that's this area, right? So I need to find that area. So what I need to do is I need to standardize this value in order to use the table. So I know Z is X minus mu over sigma. So Z is going to be 17.21 minus 16.3 divided by 0.2. Let me grab my calculator here. Something tells me we're not going to have that nice two decimal place situation anymore. 17.21 minus 16.3 divided by 0.2 is, oh, I guess we do. Z is 4.55. Okay. Already, because we know that Z has a standard deviation of 1, already I can tell that this area beyond 4.55 is going to be very, very small, right? And so what we get is we see that if we go to the table, and I'm not going to copy it in because it would require the entire table, but I need to go to the positive Z side, which I can see here because there are no negatives. And so I try to find 4.55, and I notice that I max out at 3.49. Okay, and so, and this is 9 here. So 3.49, okay, what am I supposed to do here? And this is where a lot of people get stumped, right? What am I supposed to do? Well, the only thing we can do, right? If we draw this distribution, Z is centered on 0, then I have, sorry, let me see here. There is area all the way to infinity, right? But from 4.55, I notice that the table maxes out at 3.49. Okay. And that's just a limitation of the table. Of course, if you use software, then it would know what the area is for 4.55. And so to show that the area to the left here, I draw a line up with an arrow over. So I use these arrows to indicate the area, because otherwise, if you're shading over a bunch of areas at the same time, it gets really messy. And so here, I'm going to have 0.9998, which means that this area is 0.0002. All I really know is that, so here I'll make a note. We notice the table maxes out at Z equal to 3.49. Just making a little note here. And so what can we do? Well, all I really need is that, okay, well, 3.49 is here, and I know it has an area to the right of 0.0002, right? But I actually want the area to the right of 4.55. All I really need to say, and am able to say, is that it must be less than 0.0002. Less than 0.0002, which you would say it like this, less than 0.0002. All right, because you make an L with your fingers, and then you read it this way, and that's, well, if you're looking at it the same way, that's the less than symbol, right? So less than 0.0002. So therefore, the proportion of boxes that weigh more than 17.21 ounces is less than 0.0002. Right? Therefore, the proportion of boxes, and I'm trying to keep it on the same page, so I'm going to use one line to write it out. The proportion of boxes weighing more than 17.21 ounces is less than 0.0002. We can use probability notation, right? We can use probability notation for example, here, if Z is 3.49, the probability that Z is less than 3.49 is 0.9998, which is that value there, right? If Z is 3.49, then this 0.0002 is the probability that Z is greater than than 3.49, which is 0.0002, which is that value there. Okay. So there's kind of proper ways of writing it and kind of shorthand ways of writing it. And that's okay, as long as you keep track of what it is, remembering that those areas under the curve are actually probabilities, then you should be using probability notation, but we don't have to. We can kind of get away with not all the time. Okay. Well, after the, let's see here, 17.21. Let's see here. Let's see if I can find what you mean. Do you mean the 16.3? Oh yeah, my very messy writing. Sorry. The proportion of boxes weighing more than 17.2 ounces is less than 0.0002. Sorry, messy writing. Awesome. Okay, so what if we want to find the proportion of boxes that are going to weigh between 16.11 ounces and 16.61 ounces? Okay, we have to tackle this the same way that we were tackling the other ones, and I'm going to do it by drawing the graph and figuring out a way that I can solve these. One thing I would do is just think of these areas as puzzle pieces, right? Remembering that they have to add to one total. You can kind of do whatever you want, whatever makes sense to you. As long as we get the same answer, which we will, it doesn't matter how you solve these. I'm going to show you one way, but there's lots of ways that you can do it. So let's draw it out first of all. So it's still a normal distribution and it's still centered on 16.3 and the standard deviation is still 0.2. Notice that once we establish a question, then the normal distribution that we start with doesn't change, right? And so that comes from the initial question that we're answering. And then the measurements, the X values that we're interested in come from the questions. So what proportion of boxes will weigh between 16.11? So what I'm going to do is I'm going to call this kind of X1 and 16.61 ounces. I'll call that X2, right? Because now I have two measurements that I'm interested in. 16.11 is less than 16.3. So I'm just going to put it somewhere that's less than 16.3 because it's just to visualize, right? So I'm not going to spend any time trying to figure out where it should go kind of properly. Okay. So 16.11 is less than 16.3, and then I'm going to do 16.61 is larger than 16.3. So the area that I'm interested in is the proportion of boxes between these two values. So here, the proportion of boxes between Well, the proportion of boxes between these two values is going to be this area, right? So that's the area that I want. How can I do that? How can I find that? There are many ways that we could solve this, right? And the key is to remember that you have puzzle pieces, okay? So I'm going to tell you how I solve it, and then I'll just talk about, some of the other options. But I encourage you to look at this and figure out what would make the most sense to you to solving this. Would it be, for example, I guess I'm giving the examples now. Would it be, for example, knowing that the total area is 1, and then you could take away the areas that you don't want? That's fine. What I like to do is, or you could do something weird like, the area that splits this distribution on either side is 0.5, and then I could take away the tails, then I could add those up. That seems weird. It's something that you could do though. How I solve these is I use the Z table, and I know that the Z table only gives me the area to the left, right? So what if I, let's see here. What if I find this area, which is that entire area to the left of 16.61, and then what if I subtracted this area that I don't want? Okay. I can do that because that's going to give me the area that I do want, right? If I find this total area to the left and then I subtract this area to the left, I'm left with the area that I want. It's really important that you keep track of which is which, but this is going to involve 2 Z-score calculations, right? And so let's call them Z1 and Z2 to match X1 and X2, which I set up on purpose, right? And so here, Z1 is X1 minus mu over sigma. So Z1 is 16.11 minus 16.3 divided by 0.2. And you know what? Oops, did not want to move. Okay, that's fine. I'm going to do them side by side instead. Save myself some space eventually. Okay. So Z1 is going to be 16.11 minus 16.3 divided by 0.2 is negative 0.95. I don't know why, but I'm always so surprised when I have these examples and the values just work out perfectly to 2 decimal places. That's by design, right? But that's not always the case. Then I'm going to find Z2. You could go ahead and find the total areas that you want right away, and that's fine, but I just want to do the calculation so I'm at the same point in the page for both of these. So Z2 is going to be X2 minus mu over sigma, which means that Z2 is going to be 16.61 minus 16.3 over 0.2. 16.61 minus 16.3 divided by 0.2 puts me at 1.55. So Z2 is 1.55. Let's show off a little bit. Let's use the Z table, but use probability notation to denote the probabilities. I'm also going to put the probabilities above the lines here. So I'm going to start with Z1, which is going to be able to find the area to the left of 16.11. right? Because that's the same as the area to the left of negative 0.95 on the Z curve, right? So if I go to negative 0.95, then I need the negative side. If I go, and here, I'm not going to copy this whole thing in because it's too big, but I need negative 0.9. So notice how it really helps if you can kind of have some sort of straight edge, or if you're on a tablet, right, it's easy to kind of start fresh, erase it, and work through it, right? But you need to be able to reuse the table if you have a printed copy. So that's when I would suggest, you know, you get a ruler or the edge of a book or a piece of paper or something to help you keep your eyes straight, because there's a lot of values in here, right? And it can get confusing. They are just increasing, right, as we move through the Z curve, but that takes a while to get used to. This table in particular has the different shadings and it's supposed to help you, but I find that highlighting it helps me even more. So I had negative 0.95, I think it was. So my intersection then is going to be 0.1711. So I have 0.1711. How do I write that? So you could write it out in words using the Z table, right? And that's usually how I do it for Stat 121 and 124, but you guys are more advanced mathematically speaking. So you guys should be able to handle probability notation. So instead of using that long blurb, I'm going to use probability notation and say that the probability that Z1 is less than negative 0.95 is 0.1711. Okay. I do not want to see things like negative 0.95 equals 0.1711. There's no universe where that's true, right? And so then if I see that, it makes me mad, but also it's not true, right? So you're doing illegal math. Okay. How about if we focus on Z2, 1.55? So now I'll change my pen color here. So now if I go to the tables, I can erase this because I did what I had to do there. And now I'm going to go to 1.55, which is on the positive side. 1.55. And I find that the area to the left is 0.9394. So I'm going to jot that down. 0.9394. There wasn't any room above the line, so I put it below. Which means that the probability that Z2 is less than 1.55 is 0.9394. So now I want to find the area between these two. So if I know that the area to the left of 16.61 is 0.9394, then I just need to subtract the area to the left of 16.11 to find the area that I want. So how can I write this? The probability that Z is between negative 0.95 and 1.55 is 0.9394 minus 0.1711. 0.9394 minus 0.1711 puts me at an area of 0.7683. which you can write out as an answer, right? Therefore, the proportion of boxes between 16.11 ounces and 16.61 ounces is 0.7683. Okay. So 76.83% of boxes are going to be between 16.11 ounces and 16.61 ounces. It's up to, the manager to decide or the owner to decide if they're happy with that, but that's how you would find it. Okay. That value. Deciding if we're happy with that value or not is not really a statistician's job. A statistician's job and a data scientist's job is to just report the values and potentially provide a little bit of insight if you're on the data science side. But for statistics, we're very firm on only providing values, right? We don't typically tell you what to do with these values. We're very careful not to say, oh, you need to make adjustments, because we don't know how much that costs and things like that. Whereas a data scientist would have some background knowledge because you're typically working on the entire project, and then you would be expected to provide some insights, some more insights there. But in general, we just stop at the value, right? Just kind of there, we did it. Okay. Another way that we could show this work, okay, and this is going to be a little bit weird if you haven't seen it before, and I don't think I introduced it in the video, but another way to show this work is to manipulate the original statement. Okay, so for example, we want to solve the probability that some box is between 16.11 and 16.61. Okay, so what I mean by manipulating the original statement is this is what we want to find. So what can I do? I can morph all of these by applying the same, because this is just an inequality. So if I apply the same manipulations to every portion, then it stays equivalent, right? So if I subtract the mean, for example, from each of these three sides, and then I divide each value by sigma, right? Getting to a Z-score, right? Then as long as I do it for each of the sides, they're going to be equivalent. As long as you're not multiplying or dividing by negative, right? That would change the inequality, but we're not gonna worry about that, right? Because the only way that would happen is if you divide by a negative standard deviation. That's the only division that happens here. And standard deviation has to be positive, right? There's no negative spread. So we're okay to go ahead and just manipulate these inequalities. So this is the same as the probability of 16.11. And then I'm going to do minus mu is between x, and then I'll leave a space for minus mu is less than 16.61. Leave a space for minus mu, because I realized I don't want to be switching colors the entire way, which is the same as the probability of 16.11 minus mu over, and then I'll leave a space for sigma is less than x minus mu, and leave a space for over sigma is less than 16.61 minus mu, and leave a space for over sigma. Over sigma, over sigma, over sigma. notice that this x minus mu over sigma is equal to z, right? And mu is 16.3 and sigma is 0.2. So then if I substitute that in, and I'm going to bump this up just to one line because I want to keep it together. This is going to be the same as, and maybe what I'll do is I'll work around it here. The probability of 16.11 minus 16.3 divided by 0.2 is less than z, which is less than 16.61 minus 16.3 over 0.2. I'm trying to keep it on the same page so I just don't have one line on the next page because I'm running out of time here, but this is going to be the same if I do 16.11 minus 16.3 divided by 0.2. I already found that value, right? It's negative 0.95. So this is another way to show this work, right? If you're comfortable with probability notation and working with inequalities and stuff like that, then this might be your preferred way. Okay, and so this is going to be the probability of negative 0.95 is less than z, which is less than, what was it? 1.55. And that probability is, I'm gonna need just one more line. I'm just gonna bump this up just one more. Technically, I need two more lines, but that's okay, which is the probability that z is less than 1.55 minus the probability that z is less than negative 0.95, which is the same as 0.9394. Should have given up a long time ago. Keeping it on the same page, minus 0.1711. Which is the same. So that's just another way that you could write out this problem if you prefer to solve it that way. Otherwise, it's totally fine if you just want to calculate each of the z-scores individually and find the probabilities individually and then put them together to solve the rest of the problem. That's totally fine as well. Okay. So we do have more problems, but I'll just give those to you in the video for tomorrow. So for the video, we're going to solve the remainder of the problems as well as talk about QQ plots, which is just a way of figuring out if something follows a normal distribution or not, right? Or a way to visualize it other than a histogram. And then we'll start on the binomial distribution and then we'll revisit the geometric distribution after we've done the binomial next week, other distributions. If you have any questions, let me know. Otherwise, I hope you have a great weekend and I'll stop this recording.